All right, so we are in our last section of chapter 5 that we are covering. So we are going to be, with this lesson, we're going to be identifying independent events. We're going to use the multiplication rule for independent events and then compute at least probabilities. So let's get rolling. Okay, so two events are independent if the occurrence of event E in a probability experiment does not affect the probability of F. So one thing cannot affect the probability of the other happening or not happening. They can't affect each other at all. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of F in any way. We'll look at some examples and hopefully that will help here. So independent or not first. Suppose you draw a card from a standard 52 card deck of cards and then roll a die. The events draw a heart and roll an even number are independent because the results of choosing a card do not impact the results of the die toss. So the only way that one would affect the other is if when I pulled the card, maybe the dice hit the card while I was rolling it or something, but otherwise they are completely independent. As long as they're not interacting with as long as they're not interacting with each other, they are completely independent. Next. Suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year are independent. So these are randomly selected women. They're not likely to be, think about the number of 40-year-old women in the United States. What is the probability that we're going to end up with two neighbors or something, or two people in the same household? They're most likely do not know each other. Their lives do not affect each other, so they are completely independent. Here's a contrast to that. So suppose two 40-year-old women live in the same apartment complex. The event woman 1 survives the year and woman 2 survives the year are dependent. Now this doesn't mean that woman 1 dying really affects woman 2 dying, but they are likely to encounter each other, be in each other's lives. They, because they come across each other, and one thing could affect the other, because we can't guarantee that they're completely independent, we have to say that they're dependent. So I want you to try each of the following and see if you get them right. So here are some examples. Suppose you flip a coin twice. On the first flip, it lands on heads, and on the second flip, it lands on tails. Are these events dependent or independent? If you said they were independent, you were absolutely correct. Next, are the events earned a bachelor's degree and earned more than $100,000 per year dependent or independent? They are definitely dependent. You can't say that a person can't earn $100,000 per year without a bachelor's degree. You can't say that there's, that it's impossible. However, if a person has a bachelor's degree and earns $100,000 a year, you can't say that one thing does not have an effect on the other. Next. Two 24-year-old males in the United States are chosen at random. Male 1 gets into a car accident during the year. Male 2 gets into a car accident during the year. Are these events dependent or independent? These are independent. They are randomly chosen 24-year-old males. You think about all of the 24-year-old males in the United States. They randomly chose 2 of them. So they are independent. They're not likely to be 2 people living in the same household or the same apartment complex, probably not even in the same town. So these are independent events. So it is really important to think, do they have an effect on each other? I also want to warn you ahead of time, for some reason, the probability unit really likes to, everything is death. Everything talks about people surviving or dying or whatever. And I think the reason for that is because people use this type of math a lot when they do actuarial work, which is assessing risk for insurance companies. And so that, of course, it involves death and accidents and things. So there's going to be a lot of like death questions, unfortunately. Okay, let's move on. The multiplication rule for independent events, right? If two events are independent, then we use this rule. So remember the last thing when we were doing the addition rule, it said E or F. This is an and. So it's the probability that both things will happen. So the probability two things will happen that are independent. So it's like the probability if I roll a dice, the probability I get a 3 on the first roll and the probability I get a 3 on the second roll. Independent events, and it's and. Both things have to come true. So for example, probability of rolling a 3 and 3. So that would be 1/6 times 1/6. So the probability of rolling a 3 on both rolls would be 1/36. Remember with fractions, we multiply straight across. Can you use your calculator? In fact, I encourage you to use your calculator to calculate these things. Let's do some examples. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186% according to National Vital Statistics report, that one. What is the probability that two randomly selected females will survive the year? So it's the probability two will survive. So the probability that one will survive is 99.186. The probability the second one will survive. These are independent events. So they do not affect each other. Oh, look at that. I was making it all pretty. I was writing it down. So the first female, it's 0.99186. So we do the first survives times the second survives. Remember, they are the same number because they're independent. They're both 60-year-old females. We multiply those two together. So the probability both of them will survive is 0.9838. Notice that number is a little bit smaller than the original, but because neither one is 100%. So I would like you to try this one on your own. So suppose you flip a fair coin twice. What is the probability you obtain a head on both flips? That is a head on the first flip and the head on the second flip. So probability H and H. Go ahead and pause this, give this one a shot, come back and we'll do it together. All right, hopefully you paused that. So with the probability we get heads the first time is 0.5. The probability we get heads second time, because these are independent, it's still 0.5. So 0.5 times 0.5 would give me 0.25. So its probability of getting heads on both flips is 0.25. So 1/4 probability that we will get heads on both of them. Hopefully that makes sense to you. If you have questions, make sure you send me an email or a message. Let's try another one. So a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. There's a 1-year warranty on the equipment. What is the proportion of customers that will actually make a valid warranty claim? So I would like you, go ahead and give this one a shot on your own. And then, give this one a shot on your own and come back, or pause it and then come back. Oh, and we're going to assume that the defectiveness of the equipment is independent of the use of the equipment. So it's the probability, that it is defective and used. So it's used by the customer and it's defective. So go ahead and give that one a shot and see if you can figure it out. And pause and give that a shot and come back. Okay, so we know that the probability that it is defective, so the probability it is defective is 0.1. The probability the customers use it is 0.3. So we multiply the 0.1 times the 0.3, and we get 0.03. So basically there's a 3% chance that the person is going to use it and that it's going to be defective. So based on this, about 3% of the people will make a valid warranty claim. So do you think that it is worth it to the company to spend extra money to try to make their 10% even less? Or do you think that maybe it is worth the risk, that probably is going to cost them more to fix it, that 10%, than it would be to just let it go? Okay, so we just went there. So we're going to talk about at least probabilities. So this is probably the thing that has caused the most trouble for students in the past. So I'm hoping that I can get it to you clearly. If not, make sure you ask me questions. So this is a little bit different. So listen, I'll read the problem and hopefully I can talk you through it. And also take a look at it in your book. It is the very end of section 5.3, and maybe that'll help you as well. It's right before the problem set, at the very end of 5.3. Since I don't know which book you have, which edition of the book you have, I don't want to tell you the page number. But if you're confused, I have a 4th edition and I have the RCC one. So if you need help finding that page number, send me a message and I'll let you know. So compute the probability that at least one male out of 1,000, aged 24 years and up, will die during the course of the year if the probability that a randomly selected male survives the year is 0.996. Okay, so when we're doing at least probabilities, what we're looking at is, so we're looking at least one survives. That means that, at least, at least one male will die. So we're looking at one male dying. So if at least one dies, that means that all will not survive, right? So if at least one dies, so we need to calculate all surviving and then do 1 minus that. Because what we're saying is not all are surviving. So we need the probability at least one dies, which is the same thing as the probability not all survive. So remember when we were doing not something, we would do the complement. So what we were going to do is 1 minus the probability that all survive. So we do 1 minus the probability that all will survive, because we're saying not all are going to survive. So the probability that all survive, so the probability one survives is 0.9986. So the probability all survive would be 0.9986 to the 1,000th power. Because remember, we're multiplying 0.9986 by itself 1,000 times. So when we put that in our calculator, I'm going to do 1 minus 0.9986 raised to the 1,000th power. Gives me 0.7536, or 1 minus 0.9986 raised to the 1,000th power. 1 minus 0.2464. So the probability that at least one will die is about 75% chance that at least one of those males will die. So it's 1 minus all surviving. So I want you to try one of these on your own. I have another problem I'm going to give you. I want you to try one on your own and then come back and we will work it out together. So here's the problem. So among 21 to 25-year-olds, 29% have said that they have driven under the influence of alcohol. Suppose that we took 3 of them, are selected at random, What's the problem? At least one of them has not driven under the influence of alcohol. So at least one of them has not driven under the influence of alcohol. So what we're saying is, what is the probability that not all of them have driven under the influence of alcohol? So the probability not, wait, hold on here. I'm going to write this. At least one hasn't. I can't write while I talk, apparently. Hasn't. That is the same thing as the probability not all have. Okay, go ahead and pause this. Try this one on your own, and then come back and we'll talk about it. Okay, hoping you tried this on your own. So the probability not all have means that 1 minus the probability all have driven. All have DUII. The 1 minus the probability that all have means that not all have. So I'm going to do 1 minus 0.29 raised to the third power because I took 3. 1 minus, because I picked 3 random guys, or I say guys, but random people, sorry, raised to the third power. It gives me 0.024389. So 1 minus that number is approximately 0.9756. So there's a 97.6% chance that at least one of them has not driven under the influence of alcohol. I hope that makes sense to you. If you have any questions or you're confused or your homework is confusing, send me a message. I'll do the best I can. Thank you.